Alright, now we're into the software here. I just whipped this up fairly quickly to just give a quick example or a brief example of how to implement a frequency counter. So the first thing I do is I typically declare all of my include files here. This one is a file that I wrote myself, and it includes some global variables or global definitions that I might use in other modules as well. I just wanted to be synchronized. And the most important one that's in here is the definition of the oscillator frequency, the main oscillator frequency. And in my case, it's defined as 20 megahertz, and that's what this file is here for. I'm using the util delay here that comes with the compiler, because I'm going to be I use a delay for I'll show you down below in the code here, but I just use a delay function here, and it requires this oscillator frequency to be defined. AVR IO, it just defines all of the registers and IO ports and all the different registers in the different peripherals, and it follows the data sheet very closely. So all the names that for the different registers and for the different bits in each registers are used. They're the same names that are used in this file here. And that allows me to write down things like this here. For example, this is timer counter control register 1. So this is the timer counter number 1, and this is the control register A, and this is control register B. And these are the names that are actually used in the data sheet. And so these are already predefined by the by the writers of the compiler, and they're defined in this include file. I'm going to be using interrupts here, so I need to include this library as well, called interrupt.h. I'm going to be using an ASCII an ASCII conversion routine that's also predefined, and it's in this library standard lib. And then this library here, delay, just allows me to give some time delays. Basically just makes the microprocessor waste time. I'm outputting the value of the frequency to a liquid crystal display. So this is my library that I wrote for the liquid crystal display that I'm about to use. Now here's something that probably most of you haven't encountered yet. I'm defining a variable type here, and that's what type def means. So what it means is everywhere it sees this, actually this one here, it means it's a variable type, and it can be the same as a car, or it does the same thing as a car, but it allows you yourself to define a particular type of variable. And it's a union. So what a union means is I can define access to a piece of memory. In this case it's just 1 byte, but I can access it in 2 different ways. And the 2 different ways is through this data structure, which allows me to access individual bits in that byte, or as a car, and I can access the whole byte at once. And I'll show you how that's used here. So this doesn't generate any code. The compiler just remembers this definition. And now down here I'm declaring that variable, and it's called flags, and it is of this type, flags type, and it will look like this, and it'll have 1 bit in it defined as data ready, and another bit in it defined as last sec, and then all these bits here defined as 2, 3, 4, 5, 6, 7. Or the byte is defined as the name val, and I'll show you how that gets used in a moment. I'm declaring 2 bytes here, sec timer and freq counter, and I'll show you where those are used. And I'm declaring these as volatile here, and these are global declarations of these variables within this file. They're only visible within this file, but they are visible everywhere in this file, so any function can access these variables. And I'm telling the compiler that they're volatile, which means that they may be modified in one place in the code and used in another place in the code. If you forget to put this volatile in front here, you may not have access to this variable somewhere in your code. It just makes the compiler make sure that this variable is visible everywhere. So now I've got a couple of defines here, and this one here called 1 sec gate or 1 second gate, it defines the number of overflows of timer 2 in 1 second. And if you do the math, like I mentioned here before, so the timer is clocked from the 1024 tap of the prescaler, so that means it's 20 megahertz divided by 1024. And that gives you a tick every 51.2 microseconds. In 1 second, there are 19,530.25 actually, I believe is the number, 51.2 microsecond ticks in a second. And as I said before, 256 of these ticks will produce a rollover in the counter. And therefore, when you plug in the numbers into the calculator, you come up with 76.29 rollovers of that counter occur in 1 second. And in order to make my 1 second window accurate, I could just use 76 and just ignore this extra bit here. But I chose to do it a bit differently here, a bit more elegantly, and I used this 0.29 as well. So the first count here is how I achieved the 76. So it's just 512, the inverse of 512 51.2 microseconds, 1 over that, and then divided by 256. And in order to keep all the digits here, I used 512, and I used 10 million instead of 1 million. 1 over 1 microsecond is 1 million, or 1 over 1 micro is 1 million. 1 over 0.1 micro is 10 million. So that's where this number comes from here. And because I'm doing integer math here, if I do this in the wrong order, I could end up with actually a 0 value here. But I have to do it in order by dividing this really big number by these next two smaller numbers. And anyways, the results are 76. The 0.29 is truncated. It doesn't show up in this math. And this last sec is the definition of the value that I'm going to put. So let me explain how that counter is going to operate. It's going to produce an interrupt every rollover, and this 76 will get decremented to 75, 74, 73, 72, etc. down to 0. But there's still a little bit more time left over when it gets down to 0, and that's the 0.29. So I figured out what percentage of 256.29 is, and then I subtract it from 256, and that gives me 182. So what I do is, after the last count of the 76, for the last time, I plug in 182 into that timer counter 2 instead of 256, and that gives me the last number of 51.2 microsecond counts to give me that the last little bit of time to give me an exact 1 second timeout. And I'll show you how I use these two numbers here. Here's a subroutine or a function that I've declared here that simply initializes timer 1. And if you look into the spec sheet for the microcontroller, you will see what these different values are. There's different bits in each of these registers. If I set all of the bits in this register to 0, the counter is simply an incrementing counter. So every time you tick it, it just increments. And it just keeps incrementing every time you tick it. The B register here, it selects which input is being used to clock the counter. And in this case, when it's set to 0, there are no inputs to clock the counter, so the counter is actually turned off. It will not increment no matter what's going on. I will eventually put another number into this register that will tell the counter to select the, in this case for timer 1, it will select the external T1 pin, and then it'll start clocking from whatever signal's on that pin. That's our signal that we're trying to measure the frequency of. TCN T1 is just the counter register that gets incremented. I just clear it. I set it to 0. On reset, it is actually, I don't know for sure if it's actually cleared on reset or not. I think it is, but I just did it here anyways. This TIFR1 is the timer interrupt flag register. So and there's a number of bits in that register, and it can generate interrupts in different ways. The overflow is one of them, and that's one of the bits in that register. So what I'm doing there is clearing that register. Just make sure that there's nothing in it, and you simply clear that flag, timer overflow right here. You clear that flag by writing a 1 to that particular bit in that register, and that clears that flag. This is what's called the timer interrupt mask for that timer, and if a bit corresponding to the interrupt that I want to detect is set, then that when that condition occurs with that timer, the interrupt will be generated. And so here what I'm doing is setting the timer overflow interrupt enable bit. So I'm now enabling the timer overflow interrupt by setting that bit to 1. And I didn't explain previously what this BV means. What it actually looks like is you're taking a 1 and you're left shifting it, by the value of, well, in this case T0IE1. And if I click on it here, my Atmel Studio will show me that this is how timer, I can't think of the word of it right now, how this is defined anyways. It's actually given a value of 0. So what's in here is, this is 0. So what it means is you have a 1 bit shifted left 0 positions. So you just have a 1 in there. So if it looks like this, 0B, so you've got 2, 3, 4, 5, 6, 7 zeros in front of it and a 1. Is that right? 1, 2, 3, 4, 5, 6. Oops, need another 0 in there. Okay. If I put in a 3 here, for example, that means shift the 1 bit left 3 positions. So the 1 bit is 0 shifted, shift once, 2, 3. So what it'll look like then is you'll have a 1 here and nothing, a 0 there. So that's what this BV here means. Or underscore BV. It's defined by the compiler that I'm using here. It's already there. You don't have to define it yourself. And it's just a shorthand way of creating a single bit set in a register. Let's just clean this off and continue on. Now let's look at the timer 2 interrupt or initialization routine. It is essentially identical to the timer 1. They have the same registers. The only thing that's different is the register names changed to 2 instead of 1. And as with timer 1, I want the overflow interrupt to be enabled as well. And again, to turn this timer on, I'll have to write a different number into this timer control register B. Down here, I've got 4 very simple functions that do just that. So, for example, this one here is timer 1 off. I write 0 to that control register B. If I want to turn the timer on, and I know that I'm going to be using the T1 or the external pin to clock the timer, when I turn it on, I give it this code here. These last 3 bits have to be in this particular code. And it tells the timer counter to use the T1 pin, and on the T1 pin's falling edge it will clock it will clock the counter, and it will increment the counter. And the same thing is done here for timer 2. I just put a 0 in there to turn it off, and then here I put in these 3 bits here, and these 3 bits just define that I'm going to use the 1024 divide prescaler tap. Now you will notice here I've got this little statement above. What it means is that the compiler will always make this function inline. Now these functions are very simple. I'm simply putting a value into a register, and the compiler will compile a single ATmega instruction which does this. And I need these functions, all four of them here, to execute very quickly. I don't want any overhead. So instead of declaring them as a normal function where there's going to be a call and a return overhead, it takes more time and more code. For example, when you declare a function that's not inline, it will be a piece of code that sits in a particular place in memory, and when the function is called in your software somewhere, the compiler compiles an instruction that says call that subroutine. And what the call does is it creates a branch, so the program counter goes to the address of this function. It also saves the address of where this call instruction was on a stack inside. It's some chunk of memory that saves information. And then the microcontroller will execute whatever code is in your function. And at the very end of the function, the compiler puts in an instruction called return. And what return does is it goes back to the stack and it removes the value of that of the call location and puts it back into the program counter, so then the microcontroller can go back to where it was called from and continue on. And that way that piece of code gets used over and over. You can call it many times in different places in your software and only use one piece of code instead of having to write that code many times and actually using up too much memory that way. But in this case, I don't want the overhead, the time. It takes time to do a call and a return, and I don't want that overhead. And because this function is so simple, it really is just one instruction. So what I've told the compiler to do here is to make that inline. So wherever this function is called, the compiler will simply substitute the single microcontroller instruction that writes this value to this register. And everywhere this thing is called, it'll do that. The compiler will do that rather than creating a call and a return. And all four of these little functions are done the same way. That's what this attribute always inline means. It's just simplifies the way the function is used and makes it run a bit quicker. Now, I've written a couple more simple functions here, or one more function here called getTimer1. All this does is returns an int, and it just returns the value of the 16-bit register timer counter 1. Now here I'm declaring my two interrupt service routines, and this is how you declare them in the software. You use ISR and then timer1 overflow vector, and this just tells the compiler where to jump to when an interrupt is, or when this particular interrupt occurs. And I just simply this is like a function like I've created up here, like one of these init functions. It's a piece of code that exists in memory, and it gets executed every time this function is called. Well, the same thing occurs here with this timer, or this interrupt service routine. It creates a function and stores it in memory in this particular location, and this statement here just tells the compiler where to put or where to direct the microcontroller when this particular interrupt occurs, and it gets directed to this little function here which simply increments this variable freak counter, which I declared up here. If you remember earlier, there it is there. And that's all it does. So every time timer1 overflows, this variable gets incremented. And this is the extension to the register, timer1 register. And I will use this value here later to create a much bigger number that gives me the total count that occurred during that 1 second window. Now here's the timer2 overflow interrupt service routine. It's done the same way as the timer1. And as you can see here, it's a little more complicated. There's a bit more going on. Now I'll just digress here for a moment. Earlier I talked about the variable flags, which I created my own variable type called flags type. And this is how you access the different parts of the flags, of the variable flags, using this dot notation here. You see that dot there. So I tell the compiler that I want to access the last sec bit in flags. That's what this flags.lastSec is. And there's and then here's the other bit that I want to use, data ready. Now these are just what I call flags or semaphores. They just send a signal, and they're either 1 or 0. I could have just declared a variable of 1 byte, a char, called data ready, and just simply written 1 or 0 into it, and declared another variable, last sec, and made it 1 or 0 as well. But this is kind of a throwback to my early days of programming, when I was programming earlier microcontrollers that did not have very much memory, and I could not afford to use up a complete byte to simply use 1 bit in that byte. So I would declare a union like this, or a variable type like I just did here, so that I could access the individual bits. And what the compiler does is it looks at this and it just declares, it's actually one instruction, and it's called a bit set or a bit clear instruction, and it bit sets or bit clears that particular register's bit that you're after. And because you've declared it in such a way, the compiler knows which bit you're after here, either this last sec bit or the data ready bit. And then down lower you'll see another way how I've cleared all of these bits in one instruction, but I'll show you that in a minute. How this subroutine works is it's quite simple really. Most of the time last sec flag is 0. So this if statement is false and none of this code here executes. So every time the timer 2 overflows, this part of the code gets called for every single time except for once, and I'll get to that in a minute. So each time this part of the code is run, sec timer, which I declared earlier, is decremented, and it's initialized to the value of 76. And I showed you how 76 was discovered. So what I do is I decrement sec timer, and then I check to see if it's equal to 0. If it's not equal to 0, and it won't be equal to 0 for a long time, none of this code will execute. And so most of the time when the timer 2 overflows, very little of this code actually executes. The only thing that gets executed for most of the time, in fact for 76 overflows, is it simply decrements sec timer. Now on the 77th time, on the 76th time, sec timer is decremented to 0, so now this if statement is true. And so what I do is I force that last sec value, as I declared earlier, you can see it here, but I showed you how I declared it, into the timer counter register. So now the timer counter register isn't 256 or 0, it's a little bit further along, and it'll click along for less than 256. And so what happens now is, so sec timer reaches 0, I force a new value into the timer counter register. Normally when this was running I never did that. I just let the timer register counter overflow and go back to 0 and start over again. But now I'm putting a new value into it. And then I set this last sec flag. So this smaller count, not 256, is less than 256. It will count out, and then the timer will overflow, and the first thing it sees is that last sec flag is equal to 1, because I set it here. So what I do is I turn timer 1 off and timer 2 off, because I'm done now. The window, 1 second long window, is now closed, and I set this data ready flag, which tells the rest of the world, or the rest of this module, or the rest of this file, that now I have accumulated a count over 1 second, and I'm ready to process that value into a frequency. And I also need to clear last sec flag here, because I don't want it to to be doing this, to execute this if statement again the next time. So I clear it here. And then the two timers are turned off, so there's no more interrupts. Now I'll go down to the main routine and show you how these two how this system works. So here's the main function, the main routine. And I haven't talked about this before because in the Arduino world, which is where I've been focusing recently, main, you don't see main when you write your code. Main is already dealt with by the Arduino system, and you just have to declare two functions, one called setup and one called loop. And all that Arduino does is, in its main function, is it calls setup and it calls loop, and that's all it does in their main in that main function. But in my main function here that I wrote, I got a bit more to do. So I'm going to be writing a string to the display, so I just declare some temporary storage for a string of 10 characters. And then I'm going to use this variable, which is it's 32 bits long. It's going to store my calculated frequencies in hertz. So I've declared these two variables here, and now I initialize my display. It's on port C. It's on the lower port of the data port of the display is on the lower port, and these are the two control pins. They're on these two ports and these pins, the RS and E pin. And then this tells me that it's a 2-line by 20 character display. That's how I initialize my display. Now I have to initialize some variables here. So sec timer, remember it's used up here in the timer 2 overflow. So I give it the value of this 1 second gate, which is this calculation here, but remember it worked out to be 76. I clear freak counter, which is the one that gets incremented every time timer 1 overflows, and timer 1's been incremented by the external signal that we're measuring the frequency of. I want to make sure it's zeroed. I don't want it to have any number in it. And then here's where I clear all the bits in flags. So I'm going to access, instead of an individual bit, I'm going to access the whole byte, and that's how I do that with val. So flags.val equals 0 means all of the bits in the flags are going to be cleared to 0. So I call my two timer initializing functions here, and then I turn them on. And then the next thing I do is I enable the global interrupts. Now remember, in the timer 2 and timer 1 initialization routines, I enabled their interrupts, but they won't do any interrupting unless you turn on the global interrupt, which is what this function does here. And it's also a pre-declared function. The compiler knows what this is already. You don't have to declare it anywhere else, and it knows what to do. And actually this compiles to a single instruction, which is a set bit in a particular register, which enables the global interrupts. And now the two timers that are running can interrupt the system here and do what they do up here in the interrupt service routines. First thing I do here is I output a little "Hi, how you doing" message onto the liquid crystal display, and I use this built-in delay function, delay milliseconds, delay for 1,000 milliseconds, which is 1 second. So this word, or this sentence frequency counter, will be on the display for 1 second, and then it drops down into this while loop, and this is where the microprocessor is spending its time, is in this loop here. And all it's doing is checking the data ready flag, and data ready flag will be 0 if there has been no accumulated count yet, but when it is 1, I know now, because it was set to 1 up here in the timer 2 overflow routine here. So I now know that there is a new frequency measurement ready to be processed. And so now I can execute this. So most of the time it's sitting here, it's running very quickly in this while loop. All it's doing is testing one bit, and then it goes back and tests that bit again. So over and over and over again, really fast, it's testing that one bit. And basically it's just wasting time here. It's burning up electricity in this very tight loop. But suddenly, after 1 second, this bit gets set, and then I can process the next frequency that has been accumulated. Now, to display the frequency. First of all, I've got to combine the counts from the timer 1 register and from freak counter. Remember, freak counter was incremented at every interrupt. Now there's something I forgot to mention here, and I'll go back to the interrupt service routines. I talked about, actually go back even further, I talked about having to write a 1-bit to clear the interrupt flag. The interrupt flag will always be set whenever the conditions that it's detecting occur, regardless of whether you've got interrupts set or not. And so that's why I clear it here, just in case it was already set, because I didn't want to generate an interrupt here. But if you have enabled interrupts and you're using these interrupt service routines, you don't have to remember to manually clear, or at least in your software, to clear the particular interrupt flag. It actually gets done automatically for you by the hardware, by the microcontroller. Now you can poll this flag, this interrupt flag. You can keep looking at it repeatedly and wait for it to get set and not use the interrupts. That's another way of using the interrupt routine. Like I said, that flag will get set whether the interrupts are enabled or not. But in that case, when you're just looking at that flag and you're not using the interrupt service routines, you must manually clear it. You must have a piece of code that actually clears that bit. If you don't clear that bit, you will just run back into the interrupt service routine forever, and or that bit will just remain set and your code will act kind of funny. So that was a quick aside here on automatically clearing the interrupt flags. Now let's get back to the counter. So what I do here with the frequency counter, now remember the freak counter value is incremented every time the timer 1 register overflows. Now it takes 65,536 counts for that register to overflow. So I take freak counter and multiply it by 65,536. And then I simply add it to what was left in the timer counter register when the timer was turned off, and that will give me the value of the total number of counts that were accumulated in that 1 second. And in the case of the way this is set up here, it can be as big a number as 8 million, which represents 8 megahertz. In other types of microcontrollers, the microchip PIC controller, for example, you can do the same thing here, but they have not have the requirement of the external clocking pin to a internal counter, to be synchronized with the main oscillator. The pin is directly connected to the counter, and you can clock that timer counter register as fast as the register can handle it. And I believe the spec in the microchip PIC parts is something approaching 50 megahertz. So you can measure frequencies using the same method here, but using a microchip controller, PIC controller, up to 50 megahertz. In fact, that little controller that I showed you was sitting on my workbench, or that little frequency counter, the homemade one that I showed you on my workbench at the beginning of this video, that is using a microchip PIC controller in there. And I've had that counter counting up to as high as above 30 megahertz, and it works reliably at that frequency. So anyways, we're using an Atmel part which has that limitation, but if you don't need to go above 8 megahertz, this thing works just fine. It's a good part on its own as well. So I have now made frequency equal to what the frequency count, what the frequency is of the frequency being counted or being measured. And now I use this built-in function long to ASCII, which just converts it into a string. So frequency gets converted into this, and stored into this string, which I declared up here, temp string. And I made sure temp string was big enough to hold all the values of 8 megahertz, so that's 6 digits. Plus, you have to have an extra one, because the last digit in temp string that this function will write is a 0, and that is what's called the null terminator. It just tells you where the end of the string is, because the string could be different lengths. It could be 5 characters long, or 8 characters long, or whatever. but the routine that displays this down here, put string in the liquid crystal display, it doesn't know how long temp string is. It only knows how long it is because it's looking for that 0, the null terminator. So just when you use this function, you've got to figure out what the maximum value you're going to be converting would be, and how long of a string it's going to be, and make sure you've got enough space in that string when you declare it. And what will happen if you don't have enough in here? The compiler doesn't know that, and so the compiler will happily put aside a shorter temp string, for example. And what's going to happen here actually is temp string is going to be declared in memory, and right behind it is going to be frequency, the first byte of frequency. And if temp string is made too short and you write it too long, some of temp string, some of the converted string done by I2A is going to end up as being part of frequency, and it's going to hammer the value in here, and you're going to have some very weird results. And this is the way C works. It doesn't find these kinds of errors very well. And if you've done that, you've declared a string, and you suddenly find something's going really weird, I'd go back and check to see if your strings are long enough to hold the whole length of the string, because that is a very common error that happens. Even seasoned programmers will bump into this error once in a while. So I've converted frequency from a binary number into ASCII characters so I can print it out on the display. I clear the line of the display, the first line, which has got where are we here? Which initially had this message frequency counter, and so almost right away, because frequency counter is on the display for a second, so there has been enough time now for the system to accumulate one frequency. So by the time this delay here times out and you drop into the while loop, the first thing it does is it's going to check data ready, and the data ready flag is probably set already by that time. And so the first thing that's going to happen is it's going to do all this conversion here, and it's going to clear that line, so it's going to wipe out this sentence and then write the frequency in the up to 6 digits onto the screen, onto the display. And so now I've displayed it. Now I want to restart for the next frequency. I want to just keep this continuously going, so I want an update every second or so. So I reset my sec timer and my free counter, reinitialize my timers, and I turn them back on. I drop out of this if statement, and I'm back into the while loop, and now I am checking for data ready to be 1, and it's going to sit here for another second. Eventually the second elapses, data ready gets to be 1, and then we do this all over again. And that's all this thing does. There's room in this code if you wanted to do something else in the software, because it's not doing very much here. This doesn't take very long to execute, and all of the frequency counting stuff is done in the background, and it gets, whatever's going on in here gets interrupted by the background, by these interrupts here. So I believe that's everything I covered in the software here. It's pretty straightforward. Like I said, it's very simple. Most of the work is being done by these two interrupt service routines. And then, well, there's a fair bit of work done here too, combining these two registers into one and then converting it into a string and displaying it on the display, etc., etc. But there's still lots of time for the processor to do many other things as well. So there's room here to expand this code into doing something else. I haven't tried it just yet, but when I finish with this segment of recording this segment of the video, I'm going to try to implement this code under Arduino and see if you can just pop it into your Arduino and use it directly. And the reason why I chose timer 2 here is because timer 0, which is what I would normally have used, timer 0 is actually used by the Arduino system already. And if I was to try to create another interrupt service routine for timer 0, the compiler would complain and you won't be able to compile your code. So I use timer 2 instead. So the next thing I'll do is try it in Arduino. So here's a quick look at the software ported over to Arduino. Now it didn't compile right away without errors. And the first thing I changed was these little simple timer on-off functions. Somehow the compiler didn't like the what was it, the static inline thing, and so I took that out and then just made these macros, which I could have done in the original software as well, would have worked the same way. And the other thing I had to change, of course, was these defines here for the gate timing, because we're using a 16 megahertz oscillator instead of a 20 megahertz oscillator, so that these numbers changed. Other than that, it compiled and I loaded it up and it ran just the same way. Oh yeah, also what I had to change here was, since there's no main function here, I had to use the setup and the loop functions, and I simply just put the first stuff in the main function of my original software into the setup, and then anything that was inside the while loop in my software, I put it into the loop function here in Arduino. And I didn't feel like trying to hook up my liquid crystal display to the Arduino, so I didn't. I just simply used the serial port and displayed it with the serial monitor on the screen. In fact, I can pop it up here and it should be working. And there you go. So every second, every time there's a new value, it just prints it out. So that is it in the Arduino world. It works just fine. No problems at all. One thing I forgot to mention here is, at the beginning of my original software, I had all these include files here, the libraries that I included, but in Arduino I took them all out because well, I wasn't using my liquid crystal display driver here, so I didn't need that, but all of these files are actually included in the Arduino system when it compiles anything that you do, so I didn't need to include them again, and so I just took them out. And another thing I want to talk about before I go here is the accuracy of the counter. I remember I mentioned earlier that the accuracy of the 1 second window, how accurate it is what determines how accurate the frequency counter is. And using software here, the window is there's a bit of inaccuracy in the window when it opens and closes. And let's see, if I scroll down to here, say we're in this loop already, we've started it up. So the window, when it's doing this conversion and printing out the new frequency value onto the liquid crystal display, the timers are off and the window is closed. So when you turn the two timers here on, actually when you turn timer 1 on, that's when the window actually opens. And so there's a little bit of an error here because timer 2 starts up before timer 1. If you could turn them on exactly the same time, that would be more accurate, but I can't do that. The error is minor because there's really only one instruction cycle between these two, and at 20 megahertz the instruction cycle is just a few nanoseconds. Let me just do the calculation here. 50 nanoseconds, so it's not going to make a huge difference in the accuracy at 8 megahertz anyways. Where the problem occurs is when you shut the window, and that occurs here in this interrupt service routine. Now when the conditions occur that the interrupt is generated, it takes some time for the microprocessor to actually generate the interrupt and vector into the interrupt vector. And what the processor has to do is finish the current instruction that it's working on. It then saves on a stack, which is just an area of memory, the address of the next instruction that it would have executed if it hadn't been interrupted. And then it has to change the program counter to point to the interrupt vector, which is an area of memory which contains another instruction which says jump to the actual interrupt service routine, so that takes time as well. Finally, when it gets into the interrupt service routine, it has to save a bunch of variables which take time. There's a number of instructions. Finally, it has to do this test here, which takes a couple of instructions, and then it turns timer 1 off, and that's the closing of the window. And so there's a certain amount of time that occurs from when the 1 second is up to when the timer 1 is actually turned off. And I'll pop up another file here, and I can show you the actual instructions. So let's look at what is called the list file. It's just the name of the your software.lss, and I've looked in the Arduino stuff and I can't find where they produce this file, and actually I think the Arduino system just tells the compiler not to produce this file. When you're using Atmel Studio, it's set up so that it does produce this. It's called a listing file, where it actually shows you the native instructions that the microcontroller executes, that the compiler puts together. So in this column here is the address in flash, starting at 0. And these are where the instructions are stored. And the first thing that's in the memory is this vector table. And each one of these 4 memory locations, well, it takes 2 memory locations, 2 bytes to store each native instruction. And each one of these is a jump instruction. And each one of these locations is a different vector for each of the different interrupts. And so I think this one here is for the reset vectors. So when you reset the microprocessor, it jumps to this, and then it goes to address 68, which is right here, which does a bunch of stuff. I won't go into that. And then these 2 vectors here are the timer 0 and timer 2 and timer 1 interrupt overflow interrupt vectors. So if we look at where F8 is, here F8, found it further, DEF68, here we go. So this is the timer 2 overflow interrupt service routine. It's the one I want to look at actually. So these are the instructions. And so once it finally gets to this is the actual interrupt service routine, which is stored at address F8, and it occupies all of this memory down to here. And as you can see, interspersed in amongst the assembly instructions is actually the C code, and it just helps you figure out what's going on here. So when it gets to the start of this interrupt service routine, what this is doing is saving some registers, so it's not doing anything that I want it to do, it's just saving some of the background stuff so it knows what to get back to. Down here, this little bit of code is where it's actually testing that flag, the last sec flag. And so a bunch of instructions has occurred before it actually gets to testing the flag, and then finally when it's decided that the flag is set, it's going to go down to 12A, which is here. And am I right? Actually, I'm wrong. That's if the flag is not set. So when the flag is set, it ends up here. So it turns off timer 1, which is just one instruction right here, and turns off timer 2, and then it should actually jump out of here. Anyways, so it takes a little bit from the time the interrupt is actually generated. It goes through all of this stuff, down through here, and oops, I'm in the wrong one, sorry. It goes through this stuff here, down to here, and then finally it executes the instructions to turn the timers off. So it actually gets there pretty quick. But still, there's a bunch of time. Each one of these is 50 nanoseconds. So there's a little bit of an error in actually turning off the timer 1 and closing the window. The window is actually open for a little bit longer, but it doesn't look like it's open for more than a couple of 100 nanoseconds longer. So I'm almost thinking that, well, I'd have to do the math to figure out what the error is there. But I think the error out of 8 megahertz is still less than 1 hertz. So it's probably doing not too bad a job of actually accurately timing out an exact 1 second window. So anyways, I won't go any more detail on this. This stuff is pretty hard to follow if you don't know what you're looking at in here. And I thought I'd bring this up just for interest's sake. and also just to tell you what the error could be like in this timer. But that's all I'm going to do about the software. This video has gone on long enough, and I think I've given you enough information to actually put something together and get something going yourself. So as always, I hope you've enjoyed this video, these two videos. They're both together rather long, but I think I covered a lot of information. If you have, give me a thumbs up. I always appreciate it. Comment if you wish. If you got any ideas for other videos that I could do, other projects I could do for you, I'll consider them. Again, as I keep saying, I don't have a lot of time. This isn't my job. I'm doing this in my spare time, a full-time job to deal with outside of this. But I do have fun doing this, and I do appreciate comments and feedback, so please do that. So stay tuned. I've got some more ideas, more videos coming out, and thanks a lot for watching, and I'll see you the next time. Take care. Bye for now.